Hello everyone, welcome to 1045 Engineering. We are here with yet another video in our Grind 75, a Better Blind 75 coding series. So today's problem is on finding the kth smallest element in a binary search tree. It's a very frequently asked question, though let's just quickly jump into the problem statement, understand it and start solving. Okay, last time we have solved the LRU cache. We'll mark it checked. You can find it in the list. Let's start with kth smallest element in BST. Okay, and if you see, this is the last problem in our medium series. So just a quick review. First we started with all the questions that were easy. We covered them all. There were many actually. Then we started with the questions that were marked medium, and then there are multiple in these rows in the 5th week, 6th week and in the 7th week. Now this is the last question in last problem in our medium series. Next, all the question and the problem statements are going to be of the level hard. Okay, let's start with kth smallest element in binary search tree. Okay, given the root of a binary search tree and an integer k, return the kth smallest value index 1 minus index of all the values of the nodes in the tree. Okay, the problem is very clear. We are given a binary search tree. We have to return the smallest value depending upon the k. So if k is equal to 1, that means we have to return the first smallest value. In this case, the first smallest value is 1. We return 1. For this example, k's value is 3, so we have to return the third smallest value. First smallest value is 1, second smallest value is 2, third smallest value is 3. Okay, so the problem is pretty clear. So before I go on and start solving, please take a minute and think of an approach that you would take to solve this. Okay, ready? Now, if you notice few things in binary search tree, the left child is smaller than the node, than the root, and the right child is bigger than the root. So there's always a possibility that we'll get a solution from the left child, but we have to find the smallest depending upon the k. Otherwise, we'll always pick up the leftmost child, right? If you see in this case, let's say k was equal to 4, we get 1, 2, 3, and 4th would be a right child. So we know that we have to first search it in the left, then we have to search in the root, and then we have to search in the right. So we can use in order traversal for this. Of course, one more solution could be that you could build a min heap such that you transfer all the node values from this tree to and build a min heap tree, and you'll always have the minimum element at the top. One by one you start removing from there, and when you have reached the value k, your top root node will be the kth smallest. And similarly, you can use the approach for the kth largest as well. But since we are already aware of this solution, let's take it with this approach. Okay. Now, what all can we notice? So we can notice that we should follow in order traversal to find our kth smallest. What we can do is, with each node, let's reach the bottommost. Okay, we have reached 1 using traversal, and since we call it recursively, it will call internally the left, then the root, then the right. So we'll check for the left, and if it does not have any child, it is null, we'll return -1. At this point, we'll increment our counter. We'll keep a counter. We'll increment our counter plus. So we'll see if the counter is equal to the value of k. For this node, it will be no. So we'll return -1 only from here. Next, when we arrive at this node, we already received the answer from the left child. We'll check the current node. Then we'll check for the right child. Since the right child doesn't exist, the current node was already count was not equal to 3. So we return -1, and we do not check anything in the right. We'll get -1 for the null. We go back to the upper node. We come to 3. The counter by now has gone to 3, and the current node will be the kth smallest value, and we'll simply return this value. We don't need to check on the right child, and this will be our final answer. Okay, so with this, let's start. Okay, first we need a variable for our count, right? So let's say global variable to keep track of the count. Okay, so we can say private int count. Okay, now in this one, let's initialize our count. Initialize count before the recursive calls. So count is equal to 0. Okay, now since we want to perform this call recursively, we'll create a separate method for the recursive call. Let's create that one first. Recursive function for which traversal is this? This is in order traversal. Okay, so what all do we need? Private int in order traversal. What all do we need? We need the node, that is the root node that is given to us. So tree node and the value k. That's it. Okay, so from here we can simply say return in order traversal, and we'll pass root and k. That's it. Let's comment for everyone. Okay, it will simply be start the in order traversal. Okay, or in order traversal till we find the kth smallest element. Okay, now let's come to our main function, which is actually going to perform the task for us. So we need a base case, as we mentioned below 1. We need to check when the node is equal to null, we'll return -1. So we'll say base case, if node is null, return -1. So if node is equal to null, you can say return -1. That's it. Now we want to traverse the left side and the right side. Left side, then the current, and then the right side, right? So we'll call for the left traversal. So we can say traverse the left subtree. Since it's recursively calling, we'll call the same method again for the left child. So we can say int left, and whatever the result comes, result is equal to in order traversal. What all do we need to pass? Since we are calling for the left child, we'll say node dot left, and k's value is going to remain same. Okay, now whatever the result we'll get, we'll check if it contains the result that we are looking for. If the left subtree does contain the result that we are looking for. Okay, so we'll check if the subtree or the left subtree contains the kth smallest. Okay, we'll check if left result is not equal to -1, because in other cases we are returning -1. So if it is not equal to -1, we can simply return left result, and the code can end here, right? And at fifth, we are checking for third. Since third is not null, it will call for second, then it will call for 1, then it will call for left child, which will come out null. In the end, we'll be calling for, we'll check the null will be returned back to the current node. Left result is not is equal to -1, since we'll be returning -1, so the loop will not enter this case, but we'll increment our count ++ for our current node, that is 1. So, or I'll say increment the count as we visit the current node. Okay, now we incremented the count. We'll check if the current node is the kth smallest, because that is the possibility, right? So check if the current node is the kth smallest. So we'll check if at this point in time count has reached k, count is equal to k, then we can return current node, that is node dot value, right? So we traverse the left for in order traversal, we traverse the current by checking this. Now we'll simply traverse the right. So we can say traverse the right subtree. So it will be returned in order traversal and will pass node dot right and k. Okay, that's it. So what happens, we are at 5, we check if node is equal to null. No. We call for the in order traversal on the left node. Okay, we are at 3. Again we check for null. No. We call the left node, we are at 2, simply we are at 1, and then on the left child we get -1 return as the left result for 1. We check if the left result is not equal to -1. In this case that is equal to -1, so this loop does not get executed. Count is incremented and count becomes 1. We'll check for if the current node is the answer. If the count is equal to k, so k's value is 3, that is not, so we'll do not return this value. We check for the, we simply return in order traversal on the right node for 1. That will also be -1, so we return -1 from here to 2. Now at 2, left result came out to be -1. We check if it is not equal to -1. It is equal to -1. It is not this loop does not run. Count is incremented, count becomes 2. We check if the count is equal to k, count is not equal to k. Then we go and return the in order traversal from the right node. Since on the right node it is -1, we get a -1 return. We return -1 from 2 towards 3. Now for 3, left result came out to be -1. We check if the left result is not equal to -1. Sorry, it is equal to -1. This loop does not get executed. We increment the count becomes 3. We check if the count is equal to k. Yes, in this case the count has reached the value k, so we return node dot value, that is 3. So we return 3's value, we return the value 3 back to the above method, which is 5. Now 5 will check if the left result is not equal to -1, that is true, so it will return the left result, that was 3. 3 will go back to 5, and in the end 3 will get returned to the base call from in order traversal. Okay, I hope it was simple and clear to everyone. Let's run it. I'm hoping no compilation issues or typos, I would say. Oh, great. Let's submit. I'm hoping good efficiency. Oh, okay, I'm hoping great efficiency. Okay, yeah, that's all from today's video, everyone. Yeah, I hope it was clear to everyone. And yes, the overall time complexity is going to be of log n for any other binary search tree. And yes, in worst case it can go to O of n when we have to visit all the nodes. Skewed tree would be that all the nodes are on the left side, or the right side. Okay, yeah, so that's all from today's video, everyone. For anything, please let me know in the comment section, and in the end, please like, share and subscribe. Thank you.